In this video, we'll try to make a practice over the position neighbors idea so that you can see how that could help you in practice. In this problem, we will read a matrix. Whenever I say read a matrix, I mean by that typically it's an integer matrix, and you read number of rows, then you start to read row by row, which could be like maybe the column, maybe seven values, 8 values, whatever, but all of them will be same number of columns. This is what I mean by read a matrix. And then I would like you to print all positions that are a mountain. The mountain is defined as following. It is a position that is bigger than all of its 8 neighbors. For example, in this matrix here, we notice that the 8 doesn't have 8 neighbors, but have 6 and 2 and 3, and it's bigger than all of them. So 0, 0 is one of the outputs. 9 on the other side also is bigger than the 1 and 6 and 2 and 6 and 4. So also as another mountain. The 6 here is less than the 9, so it is invalid mountain. Give a trial to code that and make use of the 8 neighbors code that we learned before. Here is a simple code that is going to read for us a matrix. I'm reading the number of rows, verifying that the rows is greater than 0. I am computing a list of 0 times rows. I'm doing that because I would like to avoid the appending. Appending is a bit slow, so if you know the size, maybe it's a good idea to start with it. Then iterating row by row, reading integer, reading list, splitting, converting to integer, and that's it. I'm then returning rows and the length of the first row, which is number of columns, and the list of lists. This is a handy function that I use it a lot in the homework. Now let's go back to our code. I'm modifying the getNeighbors function to allow me to filter out all of the positions that are outside the grid. To do that, I did two things. I declared the function here, defined the function is within grid. It takes a position R and C, and it takes how many rows and columns in my list. And after that, it verifies if the R between the 0 and rows minus 1, and the column is between 0 and columns minus 1. If this is satisfied, then we know that R and C position is valid. Now let's change our previous code to allow us to filter the invalid positions. We can do it as following here in this commented code. This is our previous code, and I'm adding an if condition to it that as a filter. If is within grid, and passing I, di, and g, dg, and the rows and columns. This is so good. There is just one minor issue in it. Observe here, the R and C equations are duplicated. So as we learned before, the walrus operator can help us get rid of that. We can assign here the value of R to this term and the value of column to this term, and then we can just use it here. It's now making the code much more nice and simple. Remember, this operator evaluate the value and return it, so it is assigned and returned. It's called assignment expression. Now let's go to the code itself. I'm reading the matrix and handling the rows equal columns equal 1 in a bit special case, because this position will have an empty list in terms of the neighbors. Now you see here the code will be very trivial. I'm iterating on every row and the column, getting the neighbors of this guy, which will return for me a list of the positions of the neighbors, and they are all filtered. After that, I'm creating a list of all of their values. So the positions will be the positions, and this guy will be their values. And I'm taking the maximum among all of them. Finally, if the current cell value is greater than the maximum of all of my neighbors, then we are a mountain. Without the getNeighbors function and its style, this code is going to get complicated with different if-else's or different for loops. This is why this function is very handy and nice. That's all.